Hi everyone, welcome to our latest episode of GoingNative for our special Halloween edition. Ooh. What is up with the lights in this room? Oh hey Steve, are you doing that thing where you sneak up on people?
I don't know what you're talking about.
Hi everyone, I'm Gabriel, and this is Steve from the debugging episode. Steve, you are the, well, I guess the not so new anymore.
Not so new.
Dev manager for the Visual C++ team.
That's right, I've replaced Ale as the dev manager.
And apparently Ale as a co-host.
That's right, it comes with the job.
Yes.
Yeah, in addition to being the dev manager of C++, along with that great honor, you also get to be famous on the internet.
It's definitely nice to be able to work with a co-host, and especially just because as a dev manager you have sort of an idea of what's going on in the world of C++. And it's nice.
So I claim. Today we're going to be talking to Artur Loxberg. He's one of the dev leads here in Visual C++. He's actually the lead of the libraries team, but he's also a sort of expert on parallelism. And today he's going to talk to us a little bit about Parallel STL, which is a way to get the best performance you can out of your code using libraries that you're already familiar with.
Yeah, let's get right to the interview.
Hello everybody, and welcome to the latest episode of GoingNative. This is Steve behind the camera, sitting here with Gabriel, and today we are talking to Artur Loxberg. He's a dev lead here in Visual Studio.
Hey, my name is Artur Loxberg. I'm looking after a team that builds Visual C++ libraries such as the STL and MFC and others. And I've been in Microsoft for 15 years now. For most of my careers, I've been building tools for developers, compilers, libraries, and stuff like that. And today I'm mostly responsible for stuff like STL and MFC, and we'll talk about Parallel STL today.
Great. So today's topic is Parallel STL. Tell me why our audience should be interested in that.
People always say that parallel programming is hard, right? And programming is hard in general. And what makes it easier for us to program is having effective tools and abstractions that allow us to compose our programs from kind of higher level algorithms. In C++, one such library is called the standard library. If you truly embrace the standard library, then you find yourself writing fewer low-level error-prone code, such as loops and little constructs like that can be easily replaced with invocations of std-find, std-search, std-sort, etc. And so your code becomes more maintainable, easier to understand, and in general, more performant.
Great. So how does that relate to Parallel STL?
So the way that it relates to parallelism is the standard library today is completely serial. There are fairly low-level constructs that allow you to write parallel code, but they're difficult to use. So, for example, if you want to sort an array of integers, it's pretty hard to do today using the standard library. But with the Parallel STL that we are introducing, it will become much easier. And in a few minutes, I'll show you how to do that.
Great. So how do you want to start? Should we talk about syntax? Do you want to talk about the high-level design?
Let's talk about syntax first. Let's imagine that we have an array of integers. I'm going to write it as a vector, std, vector of int v, and it's coming from somewhere. Now, for me to sort this vector, what I would do is, of course, invoke the standard sort function. And this is how I do this. Std sort v dot begin, v dot end. So I'm invoking the std sort function. I'm passing the beginning of the vector. I'm passing the end of the vector. And as a result of that invocation, we end up with an array that is perfectly sorted, right? Wouldn't it be great if I could, with the same amount of effort, sort this array, but only do it in parallel, basically run it faster? And this is indeed what Parallel STL is all about. Parallel STL is a proposal that was put forward by three companies, Microsoft, Intel, and NVIDIA. And in this proposal, we are proposing to augment standard library, to add additional capabilities to perform operations on containers in parallel. So let's look at this example, and we'll see how sorting the vector in parallel will look like using Parallel STL. This is what I will write in Parallel STL when Parallel STL is part of the C++ standard, which we hope it will be eventually. Std sort. Now I'm going to write an execution policy. std par. And then I'm just going to repeat what I already did before.
That's std par, like for parallel?
Exactly. V begin, and then V end. And with this, I'm going to do basically the same thing, but the array will be sorted hopefully faster. And I have to stress the word hopefully, right? Because if this were that easy, then we wouldn't really have much to talk about. Unfortunately, there is a couple of problems here. First is, how do we know that sorting in parallel is going to be faster than doing it sequentially? Well, it turns out that when you're sorting things like integers, you really need to have millions and millions of integers for the parallelism to pay off.
Because of the fixed overhead.
Because of the fixed overhead, yes. And obviously, a sophisticated implementation would be able to determine, oh, you only have a handful of integers to sort, therefore I don't even need to spin up a bunch of threads. But even this operation of determining is going to take some time, right?
Sure.
And so there's always going to be some overhead. So that's one. And the other problem is it always safe to do it in parallel?
So whose responsibility is it to determine if it's safe in this implementation?
It's always the programmer's responsibility, right? Nothing in the standard tells us that every function must necessarily run on the single thread, right? As long as the effect of that execution is the same. And so the compiler is free to optimize it, and the compiler is free to parallelize and vectorize this code. But the compiler also has to be very, very conservative. The compiler can only do this if it can prove statically at compile time that such transformation is safe. Therefore, it's very, very hard to do at compile time, and we need the developer's helping hand to tell us, yes, I'm going to be a good boy, I'm not going to do anything strange, I'm not going to do anything risky, such as side effects and race conditions. Yes, please, it's okay for you to parallelize this. And again, this is a developer giving the system permission to parallelize. It's not an exact directive to the system, hey, parallelize it. So let me show you an example where parallelization would be unsafe. Let's imagine that I have a counter, and I'm going to increment this counter every time a comparison operator is invoked. So I could do this doing something like this, std sort. Let me put std par here again. V begin, V end. And here I'm going to put an explicit comparator operation, which is going to be a lambda expression. Int A, int B. I'm going to increment the counter plus plus, and then return A is less than B. Closing the curly.
So there's side effects.
There is a side effect, right? And the problem with the side effect is that this increment is not atomic. And it's really, really hard for the compiler to determine that you're doing something in your comparison operator that is unsafe. That's why you have to say std par. But specifically in this particular implementation, in this invocation, we're introducing a concurrency defect.
So effectively, counter's value is undefined?
Counter value is undefined. And to solve this, you would need to do something like this, atomic of int counter. And now this becomes properly synchronized.
OK, so that is really cool. I think the neatest thing about this is like how little code modification is necessary to suddenly start to take advantage of the resources that you have available to you. So like, who do you think should care about this? Like, when should I be super excited about Parallel STL?
Obviously, we all want our program to run faster, right? Because we don't like to wait. But it's also important for us to consume battery life, right? And to consume battery life, the best thing you can do is to complete running your program, right? As fast as possible. And this is what accomplishes that, right? Just finish running your program, and that consumes the battery life. So it's important, I would also say, it's important on different ends of the compute spectrum. On one end of the spectrum, you have a low-powered handheld compute device like a mobile phone. On the other end of the spectrum, you have a virtual VM in the data center, right? And you want to consume battery life, and you want to consume, you want to reduce the energy consumption in the server.
Artur, I'm sold. How do I play with this? What do I have to do next, and how long does it take until this is in C++ so I can put std par and suddenly fix my phone?
So this is still not part of the standard C++, but we hope that it will be, right? Several companies are very much interested in making it part of C++. The next target for us to get into the technical specification, and there is already called, there's a Parallelism TS, is a document written to the same high standard as the standard. but it's not actually mandatory for vendors to implement. The TS encourages vendors to experiment with the technology, and once we get enough consensus, we'll actually introduce it into the standard.
Can you show it to us?
Absolutely. We actually have an implementation available that's currently open source on codeplex. Let's go ahead and take a look. Microsoft has produced an open source implementation of the Parallel STL. It's available at parallelstl.codeplex.com, and I'm going to use that to run a few examples. So let's go back to the example that we saw on the whiteboard. Again, I already have a beginning of the program, and I'm going to declare a vector of int and put some elements into it. So let's start with 100 elements and fill it with data. This is done with the function iota that fills the container with sequentially increasing numbers. But because I'm going to use the reverse iterator, I'm going to get a perfectly unsorted container. Begin, and I'm going to start with 0. And now I'm going to call a serial implementation of std sort. Again. Let's compile this. So nothing too exciting here. I'm just going to leave it as it is and then add a parallel invocation of std sort. This is going to look like this, std. Now, because Parallel STL is still experimental, the names of the algorithms that we have introduced are now in the experimental namespace. So I'm going to say std experimental parallel and then sort. The first parameter, of course, is the execution policy, parallel par. And then I will just repeat the same as what I did for the sequential part. First, let's see if it compiles. OK, it does, but it's still not very interesting unless we actually measure the time that it takes to execute this. I have this little utility function called measure time that takes a lambda expression. And then I will do the same for the parallel version. Oh, and before I do this, I actually have to copy the original array into V2 before it gets sorted. So let me do this. So V2 equals V, and then I will sort this array here. V2. OK, this should compile. Let's see. It compiles. Let me go to the command line window and try to execute it. And now we see that both invocations are so fast, they're faster than the margin of error. So it doesn't really make a difference whether you sort an array of integers serially or in parallel. Let's make this a little bit more interesting and start sorting a bigger array. Let's say we will want to sort an array of 1 million integers. Let's recompile and see if that makes a difference. OK, going back, invocation. And that still doesn't make a difference.
More zeros.
More zeros. Let's add another 0 and see if that helps. Let's actually do it like this. So we're going to sort 10 million integers. Let's see if that works. And now we see some speed up. Let's actually see how much speed up did we get from this. 4.16. So on a machine with 8 cores, this is somewhat disappointing but an expected result because sort doesn't yield itself to perfect parallelization. The best we can hope is to go from n log n to O of log square n. But that's still a pretty significant speed up, so we get it by more than 4x. Here is a slightly more sophisticated example where we're doing matrix multiplication. The most interesting part of this sample is the invocation of parallel for each. Again, as you can see, it's the same standard library algorithm that you've come to love in the STL, and we are invoking it with std experimental parallel par execution policy, inside of which we simply invoke a function called multiply element. We are going to invoke this sample with increasingly larger and larger matrices and see if the matrix size makes a difference. So let me compile this first. Now we'll switch back to the command line window and run the program. And on the right, you can see that the CPU utilization goes up when we run the parallel implementation, And as we run matrix multiplication for large matrices, we'll see that CPU utilization goes up almost all the way when we start doing it in parallel. We are done with this. And now you can also see that on this machine where I have 8 cores, matrix multiplication of a matrix of 1000 by 1000 reaches almost complete CPU saturation. So we're almost getting 7 or 8x speed up for a single program like this.
That's great. So if people want to play with this, we have them up on Codeplex. How do they give you feedback?
We are, in fact, very interested in receiving feedback. So if you want to play with Parallel STL, please go ahead and go to parallelstl.codeplex.com. It's an open source implementation. Go fork it, play with it, send us your feedback, send us your suggestions, and if you want to influence the future direction of C++, this is definitely your chance.
That was our interview. Thought it went pretty well, and I really like the simplicity of the new library, just how it just flows like normal code, and you get the benefit of it.
Yeah, it's basically exactly what you'd expect, right? You just annotate the code that you care about, and there you go. It's up on Codeplex, and so you can go use it, and we are dying for your feedback on this. If you can find something cool to do with this, by all means, let us know down in the comments, which I assume are below me on the Channel 9 webpage.
That's usually how it works.
Okay, great. And also, this is something that we're working towards standardizing, and so, you know, participation here with this early bits can help set the agenda for the future C++.
If you guys have any episode requests that you'd like to see, feel free to, again, leave something in the comments below. Please welcome Steve. I look forward to working with him, and we're going to put out some great content for you guys. So thanks for watching. Happy Halloween.